Hi everyone, my name is Sophia Pedico, and today I'm going to be showing that this equation here is for any value of k is a solution to the uniaxial time-dependent heat diffusion equation with respect or with no heat generation. So first off, this is based off of Euler's formula, which I'm going to write off to this side here, and that says e to the ix equals cosine of x plus I sine x. Now, obviously, you can pick out which one of these is easier to write down over and over again, and it is e to the ix. And this side is really just a Taylor's expansion series, but we've just simplified it as e to the ix because that's a lot easier to write. But now I'm going to write down that heat diffusion equation, and we're going to actually show that for any value of k, this is a solution to that heat diffusion equation. So that equation says that the differential change in temperature with respect to the differential change in time is equal to alpha, which is our heat diffusion coefficient, multiplied by the second derivative of temperature with respect to the second derivative of change in x. And what we're going to do is we're going to say that this is equal to t, this equation right here, and we're going to plug that into these two values of temperature and take the derivative and see what happens. So on this side, what we're going to end up with when we plug our equation in for t and take the derivative, we end up with negative alpha k squared e to the negative alpha heat diffusion coefficient. K is just some integer, and t is our time, and that's going to be multiplied by Euler's number, raised to the I, an imaginary number, multiplied again by some integer, and x, our position in the x direction. Now, this is going to be equal to alpha multiplied by e to the alpha negative alpha k squared t multiplied by I squared k squared e to the I k x. Now, we can actually rearrange this side a little bit. I squared can be rewritten as -1, and we can rearrange that k squared too. So I'm just going to rewrite both sides for the sake of, being able to visually see here what's going on. So we'll end up with this. And on this side, we'll end up with that negative alpha. Like I said, I'm going to move that k squared over here. And this shows that for any value of x, or I'm sorry, any value of k in this equation up here, that is a solution for this partial differential equation. Now this can also be rewritten as temperature equals the sum of k equals -infinity to infinity of some coefficient c sub k multiplied by e to the negative alpha k squared t e to the I k x. And that's just a nice way to rewrite this. But there we've done it. We've showed that this function up here for any value of k is a solution to the uniaxial time-dependent heat diffusion equation with no heat generation. And in my next videos, I'm going to be going over this a little bit more and seeing where this equation takes us and what we can model with it, also in Python. So I'll see you in my next video.